Hey everyone, Sam here, and welcome to the channel. If you're new here from the Chessboard Detect video, this video is a bit different. I do live time solves of programming puzzle questions from a website called Leetcode. And while that's a bit different from the way I approach solving chessboard detection, there's actually quite a lot of overlap with how you do approaches for solving programming puzzles. And I kind of try to do it as acting as a tech interview candidate, and I think it's a pretty good way to think about how you should approach solving problems. So you may find this interesting as well. If not, totally fine. See you in the next Chessboard Detect video also. But for those who are still watching, let's have a look at this question today. We're doing a daily one called number 231, power of 2. So we are given an integer n, and return true if it is a power of 2, otherwise return false. Right, powers of 2, like 2 squared, 2, 4, and so on. An integer is a power of 2 if there exists an integer x such that n is equal to 2 to the power of x. So for example, if n is 1, that's true because 2 to the power of 0 is 1, and 16 is also true because 2 to the power of 4 is 16. N is 3 is not because 2 to the power of nothing equals 3, legally, I mean, with an integer. And we get some constraints as well here, so minus 2 to the 31 all the way to 2 to the 31 minus 1. And there's a follow-up too, which we'll look at in a second. I haven't read it just yet. Let's think about this for a second. How do we tell if something's a power of 2? There's a couple of ways we can do that. I think the most brute force direct way, let's kind of start typing it out. Make sure everyone can see this, yes. So brute force, let's call this approach 1. What does it mean to be a power of 2? It means that it is 2 times 2 n times until it reaches that number. So you should be able to divide that number by 2 indefinitely until you reach 1 with no extra remainders. I think that's the brute force approach. So like, I'm just spitballing here. So let's just say we had our number 16. If you divide it by 2, then you get 8. If you divide that by 2, you get 4. And if you divide by that 2, you get 2. And if you divide that by 2, you get 1. And that way that's a power of 2. If you had another number, like let's just say 14, which is divisible by 2, so it gets you 7. But 7 divided by 2 is not going to be equal to an integer number. It'll be 3.5 in this case. So we know this isn't a power of 2. So one approach we could do is keep dividing the number by 2 until we reach 1, or a non-int answer. Return false if so, true if we get to 1. That's the basic logic and rule. And there's some actual nice things about this one. If we do this, we are going to be doing an O of, I think, log n, where n equals the number. N is equal to n in this case. And it's log because we're constantly dividing it by 2 in this case. So this is like log base 2, I think, in this case. And this is time, and it'll be O of 1 space, which is not bad at all. I think we can do better than that in some ways. So let's just keep that in mind. This is the brute force. It's good to keep it up and out, sorry. There. It's good to know what the first approach would be. What else could we do? We could do it the other way around. It's still technically brute force. What we could try to do is take 2 and keep doubling until we hit the number or pass it. So in this case, let's say our number n is equal to 16. We take our 2, we double it, and so we get 2 times 2 equals 4, times 2 equals 8, times 2 equals 16. We've hit it, it's true. And in the case of, let's say n had been 15, then we would have passed it and it would have been false. This is the same logic as the first one, it's just a different way to approach it. One might be easier than the other. It depends on which one you want to do. This would also be O of log n and O of 1 space, and yeah, there's nothing wrong with that either. So the thing I think is useful and interesting here is what does it mean to be an int in Python? In our case, we have our constraint of 2 to the power of 31 minus 1 plus minus 2 to the 31, and that's just a 32-bit integer, which means we know what the largest power of 2 could possibly be. It'll be 2 to the power of 31 minus 1. Actually, it'd be 2 to the power of 30, because that would be 1 less than that. So there's only 30 possible numbers. So approach 3 is fixed array So let me just explain what I mean by that. And you may have already come across this. idea in your head. So the idea is fixed number of possible powers of 2, keep them all in memory, and check if n equals them is in that set. So let's just say we had our set of all powers of 2. There's only 31 of them, let's just say. In this case, I think there's actually only 30 of them because we don't have to worry about 2 to the power 31 because we can't reach that within the constraints given by this question, as well as how ints work usually for 32-bit ints. So that's a fixed size array, and it's a set, and set checks it just once. So now the logic is keep a set of all powers, check if n is in the set, which is O of 1 amortized, check, and if it is, it's true, otherwise it's false, and that's the whole solution right there. And the nice thing about this one is it is O of 1 time, and it's technically O of 1 space also, because there's only a fixed number of ints in there. We don't have to worry about, in fact, if the number n is negative, we don't have to worry about that because you can't reach a negative power of 2 with an integer. I'm pretty sure, let me just explain what I mean by that. If you had 2 to the power of -1, that's equal to 1/2 or 0.5. And that's not an integer in this case, at least according to the rules of this question. So we don't ever have to worry about 2 to the power of a negative number, or even, you can't even reach a negative number because 2 to the power -2 is equal to 0.25 or 1/4, and so on. It'll be 1/4, 1/8, 1/16, and so on. So we'll never have a negative. If n was negative or 0, we know the answer is false. So that's actually kind of a first check we could always do. I like this one a lot because I don't think we can do much better than that. Yeah. There's some other little tricks we can do here as well, which is check bits. So the other nice thing about a power of 2 is that no matter what it is in binary, it's going to only have 1 bit. Power of 2 will have one bit in it. So let's say 16 is equal to like 100 in binary, I think. 2 to the power 0 is 1, power 2 is 2, 1 is 2, power 2 is 4, 8, sorry, one more. I think this would be 16, and so 8 would be equal to 100, 4 is equal to 100, 2 is equal to 10, and 1 is equal to 1, and so on and so forth. Actually, we could get all of them this way, and there'd only be 30 of them. So you could do something like n.bitCount or something like that. I think there's a Python function for that, and that will just be technically this is going to be O of log n time search through bits. But I have a feeling it might be implemented in C and be quite fast. So it's a question whether this would be faster or slower than approach number 3. And we could implement this manually also, but it would become equivalent to approach 1 or 2. I think it's just a different way of thinking of it. These are doing the exact same thing, just in a different logic. This is more mathematical, this is more binary, which is also mathematical, but you get the idea. Okay, so I think I'm going to arbitrarily choose approach 3 because I like the idea of having a fixed size array and a simple set check. So we'll just create this array once ahead of time. And I think, I'm trying to think about how I'd like to do that. How do we want to do that? 2 to the power of I, for I in range from 0 through 31, not inclusive. And this will be a set. So this is powers of 2. So I'm creating a set using a generator of 2 to the power of that integer I from 0 through 31, 0 to 30. So 2 to the 0 will be 1, and so on. And we then just do a check for if n is in powers of 2. I don't think it's is in. I think it might just be in return. Actually, just return if it's in powers of 2 or not. And I think that's the whole logic. Generating this set takes O of log n time to to generate. It's a fixed size array, so I'd say it's O of 1 space, though maybe you could argue it's O of log n space. It's not, because it's just a bit size. I'd like to put this outside the here somehow. I think you can do it like that, and then you can approach self.powers like that. Does that work? I'm not entirely sure. Let's do a run and see. And you know what? I'm sorry I never started the timer, so apologies for that. Alright, passes the test case for 1 and 16 and 3. So it looks like this does work the way it's written. So the reason I'm putting this outside the function is because I don't want to regenerate this powers of 2 every single time. I can generate it once when the solution is instantiated, and then we just return if it's inside that or not. We don't even have to worry about negative numbers or anything like that, because I can just do a check inside the set. Let's try submitting this and see how it does. Cool, it got accepted. Not the fastest, that's tragic to see, but it's within the bell curve, so I'm happy about that. Let's think about what we could do to make this a little bit faster. Technically, doing this check is going to take some time. Maybe more importantly, we're trying to access something that's inside the solution. I have a feeling that the bit count solution might be the fastest. So here we'll just return n dot, I think it's called bit count, equals 1. If it's equal to 1, that means it's power of 2, otherwise it's not. Let's check if that's true or not with the test cases. Cool, so it was the name of the function is bit count, passes these test cases. Let's submit and see how it does. All right, come on. Oh, failed on negative numbers. That's a good point. I forgot about negative numbers for this case. We also have to say n is greater than 0 and n.bit count equals 1. Here, because we have negative numbers and integers, that'll be the first bit on the in the binary array, and that would actually be true for 0 or some negative number. Okay, let's try this again. Let's first do a check on the test cases. Passes those. Actually, should copy this over and make sure it goes inside there. Let's just test it there. Cool, passes the negative 16 being false. All right, let's submit and see how that does. We didn't need to do that for the set one. Cool, and now we're inside the center of the bell curve. Not much faster, but I think, again, we don't need to worry too much about the time here because we're within, the bell curve of how the backend implements things, but I do want to see if we could go a little faster. I'm trying to think of any other tricks that are there. As an interviewer, I would be happy to see them talk about the bit count approach. I would probably be, I think this kind of offloads a lot of work to the back end. I would love to see the set-based approach just for the logic. If there's a reason to go through these brute force approaches, maybe make the problem harder in some other way. Maybe instead of a power 2, it's some multiple of some other number or a prime or something like that. I don't know what else we could do here. I think we've kind of reached the mathematical approaches here. Is there some tricks? Let's have a look at some of the other solutions. Yeah, no, they did approach 1. They use modulo, that's great. Let's try another one. Yeah, they just loop over all the possibilities. I guess technically you don't have to generate it once at the beginning that way, and there's an argument for that. I wouldn't read too much into this. There's some interesting thing with the XOR, that's kind of fun. Oh, sorry, that's just checking the count of bits, essentially. Yeah, I like this one. This one's nice and clean. This is the second approach we talked about here, the keep doubling the number until we reach. So, sorry. That's pretty nice, I like that too. Yeah, I think I can't see anything extra special here. If you can think of anything in the comments, please let me know. But this is a pretty fun one because there's quite a few ways you can approach this. They all are, at the end of the day, the same kind of concept, which is you're trying to either multiply or divide a number to see if it's a doubling of 2. And you can either do that directly by dividing the number by 2 over and over, or you can double the 2 until you hit that number, or you can have a fixed set array that has already done that ahead of time and then check if it's inside that set. Or you can count the number of bits, which is equivalent to those just by looking at the bit counts instead. I prefer this one, I think, just because it feels the most fixed in terms of memory. There's no more dynamic memory allocation, and it feels very clean, and I could scale this up to some sort of extension problem more easily, I think. So yeah, pretty fun, and hope it was interesting for everyone watching. I'm still working on the second part for the chessboard detect video, so stay tuned for that one as well, and I'll see you all next time. Cheers. Bye.